Hello, my name is Brandon Enright, and this is a stream of consciousness video on how to solve twisty puzzles. The puzzle you are looking at here is Gelatinbrain's 1.4.14 puzzle, and it's a edge-turning dodecahedron. And this puzzle is incredibly similar to the Star Minx 2, that is Drew's Star Minx that turns on edges. However, Gelatinbrain has made the cuts slightly curvy, so they bow out slightly. So that the normal version of this puzzle, I think, just has edges, centers, and like one other centerpiece. But this puzzle, because of these curvy cuts, there's some overlap that creates a whole bunch of new pieces on this puzzle. This video is not so much about how to solve this puzzle. I think this puzzle is a very beautiful puzzle, that's why I chose it. It's one of the reasons why I chose it. But really this video is on how to solve sort of large, medium difficulty puzzles, which I haven't actually solved this puzzle, but based on some quick perusal of the puzzle, it seems to be relatively straightforward. It doesn't seem to have any really long commutators. It's not really that deep cut, so you don't really have any strange pieces that are, very hard to cycle because there's so many of them to cycle at once or anything like that. So I would call this puzzle medium difficulty. I mean, its size does not really contribute to its difficulty. It just contributes to the amount of time needed to solve it. And it doesn't have too many pieces that need orientation. It doesn't appear to have any weird orbits or anything like that. So I think it's going to be a good candidate to discuss how to solve. Now again, this is not a video on how to solve this puzzle. This is a video on how to figure out how to solve this puzzle, and I'm going to try to make this video sort of generic enough that you can figure out how to solve really any puzzle like this and figure out how to layer commutators on top of each other. So if you have a non-pure commutator and you need to layer it, a layer of pure commutator on top of it. That's what this video is about. So here's the puzzle scrambled. So I guess the first thing to do on this puzzle is take a survey of pieces. Oh, I should mention that I have not actually. I'm not looking at any notes. I have not made a pre-made list of routines. I've only spent a few minutes on this puzzle, sort of planning out how I think a solve should go, and so this is going to be as much a discovery of this puzzle as it is going to be a tutorial of the puzzle. So we should first take a survey of the pieces on this puzzle. It's got a center, so it also has edges, and the edges look like they're the only piece on this puzzle that have orientation. It has, around the center, it has this part and this part. So this is sort of looks like maybe like Gigaminx style centers. I don't think that they work like a Gigaminx at all, but you can sort of imagine this pattern on a Gigaminx face. And then it has, in between the two edges, it has this leaf, point, and then other leaf. And the first thing that sticks out in this puzzle is that this piece and that piece, they must be chiral partners. That is, that must be the left-handed version and that must be the right-handed version. And there's going to be no way to take this piece, which is a right-handed piece, and put it into a left-handed spot. Or at least no way on Gelatinbrain. I don't know about jumbling. It's an open question. So if you happen to know if jumbling could ever violate this, then please tell me. There's a bunch of intuition for why this right-handed piece could never go in a left-handed spot and left-handed piece could never go in a right-handed spot. For one of them, they're actually different shapes. So notice how this one sort of points to the right and this one sort of points to the left. There is no way to take that piece and put it there without taking the mirror of it, so like flipping it around in a mirror. And mirror operations are impossible on three-dimensional twisty puzzles. That is, if you want to mirror a two-dimensional piece, or, well, it's a three-dimensional piece, but we'll ignore the internals. There is no amount of rotation and translation that will ever allow you to mirror a piece. Now, that's not true in 4 dimensions. You can mirror three-dimensional pieces in 4 dimensions, just like you can mirror, a two-dimensional, so you have a one-dimensional line segment, and you rotate it in you rotate it in a second dimension and you can mirror it, and then you have a two-dimensional plane and you rotate it in the third dimension and you can mirror it. In three-dimensional pieces, you need to rotate in the fourth dimension, which is not available to us to mirror a piece. And so that's not going to be possible. So okay, so we know what pieces this puzzle has. We don't know what order to solve them in, but the most basic possible commutator is a 1-1 commutator. So that's one version of a 1-1 commutator. And so let's look at what 1-1 commutators are available on this puzzle. And the reason it's called 1-1 is the commutator is an x part and then a y part, and then you undo the x and then you undo the y. And because x is one move and y is one move, we just call it 1-1. It's a shorthand to describe the length of the commutator. 4 moves total. 2 of x and 2 of y. So because 1-1 commutators are the shortest possible, let's sort of take a survey of what commutators are available on this puzzle. So there's this one that I just did, and it cycles edges and centers, and anyways, it cycles pieces. And then there's that overlap. So that's probably also going to be very useful. And let's see, there's going to be this overlap, and that's sort of big and complicated and probably not going to be useful. And I think there might be another overlap, so let's see. So we do that. Okay, yeah, so here's this overlap. And that looks like it's going to be basically the exact same. This piece, either that piece or that piece, they look like they have almost the same amount of overlap. So they're probably going to be equally useful for constructing commutators. So those are the 1-1 commutators available to us. And a 1-1 commutator that has no overlap between the pieces is just utterly useless. We just wasted 4 moves. And since a 1-1 commutator is the shortest possible commutator, it turns out that the next shortest possible commutator is 3-1. And the 3 has to be a 2-gen sequence, so it has to have 2 faces, even though it's 3 moves. So that means you do a move, you do another move, you undo the first move. So that's a conjugate sequence. And after 1-1 sequences, the shortest possible sequence after those is 3-1 sequences, and the 3 has to be a conjugate sequence involving 2 faces. And so because there's only there's only that one, that 1-1, and then there's that one. Okay, excuse me. There's that 1-1, and then there's that 1-1. So, and then there's that 1-1. Those are the only things that are available for making the 3-1 sequences. Because a 3-1 that doesn't involve any overlaps like that is also utterly useless. You can do a 2-gen conjugate sequence and we just wasted 3 moves. It did nothing for us. So these are the available 3-1 sequences. And on an edge-turning cube, because clicking it twice, the inverse of the move is just doing the move again. We don't have to worry about direction, which really simplifies it. And it's one of the reasons why I chose an edge-turning puzzle, because I didn't want to have to talk about, well, there's lots of combinations. Like you turn it that way, and then you turn, So this puzzle has a relatively limited number of possibilities for the 3-1 sequences. So there would be this 3-1. So that's the 3, and then we'd have to figure out what the rest of the other 1 is, the y part. And then there would be this 3-1 sequence. So that's the 3, that's the x part, and we'd have to figure out what the y is. And then there's going to be that 3-1 sequence. So as you can see, each one of these 3-1 sequences is essentially the 1-1 commutator, the 4 moves. We just left off the last move. So it's essentially like truncating a 1-1 commutator and turning it into a 2-gen conjugate sequence. And by the way, a conjugate sequence. So a commutator's x, y, undo x, undo y. A conjugate sequence is x, y, undo x. And so you can build commutators with conjugate sequences. And you can also look at a setup move as a conjugate sequence. So here we go. So we'll do like an x part. And then we'll do x, so that's x part of a conjugate. Now we'll do the x part of our commutator, y part of our commutator, undo x, undo y. Now we have to undo the x part of our conjugate, basically undo the setup move. And we will have done a 3-cycle edge, edge, edge. I think we also made a mess of the centers, yeah. Center, center, center. So we did a 3-cycle of the edges and a 3-cycle of the centers. Okay, so enough conjugate and commutator theory. That's what we're going to use to build the sequences on this puzzle. And so let's first explore what is available via the conjugate sequence, or the 1-1 commutator sequences. Okay, so there's that one. It does a 3-cycle of this bar. Unfortunately, it involves 2 of these pieces. It looks like a left-handed version and a right-handed version of the piece, so that's not going to be so useful. And then 2 of, let's call them Gigaminx face corners. Although, again, the Gigaminx is a little bit of a misnomer. It's just the pattern and not the actual piece. And then cool, it has this Gigaminx face center edge thing. And there's only 1 of them. So ignoring the other stuff that breaks, this 1-1 commutator can solve these things as long as we haven't already solved these point wing pieces or these corner center pieces. As long as we haven't solved those and we can break them, then we can use that 1-1 sequence to solve these pieces. Okay, great. Then there's this 1-1, and sorry. Okay, let me start that over. 1, 1, 1, 1. Okay, there's that 1-1 sequence, and again, that breaks that is a 3-cycle. Well, it doesn't break them. It does a 3-cycle of the edges and a 3-cycle of the centers. Now, there are I think 30 edges on this puzzle. Yeah, there's probably 30, and there's only 12 centers. So if we're going to use a 1-1 commutator, we should use our short commutator on the pieces we have the most of. And since we have the most edges compared to centers, we should use that as a non-pure sequence to cycle edges and completely ignore. So basically we would solve edges first on this puzzle, ignoring whatever the centers are. Then how will we go about solving the centers? So we could do this 1-1 sequence and then do that. So that was we did our 4x move x part. That was our y part. Now we're going to undo our x part. Oh, excuse me, I have to start. You have to start opposite. Okay, so I just undid our x part. Now I'm going to undo our y part. Okay, so that did a 3-cycle. Center, center, center. Did a 3-cycle with centers. And that seems really reasonable since we have 12 centers. It's okay to spend, well, so we did a 3-cycle with that was a 4-1. So we nested a commutator, and so that's a really bad idea because it's really trivial to do a 3-1. So do that, do that, do that. So that's our y part. It's a conjugate sequence. Then we'll do our center, and then we'll undo our x part, which is a conjugate sequence. And then it'll do the exact same centers, but we did it in 8 moves. So it seems really reasonable to do these 12 centers in 8 moves rather than 12 centers in 4 moves, because then what option would we have? We'd have to do the edges in more moves instead. Now, the other thing is these edges have orientation. So if we do that, we didn't really get to choose what the orientation is, but it's really easy to change the orientation on that piece. So we can just do like a little setup move to change its orientation, and then undo the setup move, and that will have cycled 2 of the pieces in a different orientation. So now let's look how to make a orientation changing commutator for these edges. So again, if you've seen my other videos, it basically means, so what we'll do is we'll take that edge and that edge. So we'll put that edge and that edge a spot. Now we're going to figure out how to flip this edge around and put it back. So we're going to take that edge out, we're going to flip it around, we're going to put it back. Now it's in backwards, so the blue's on here and the green's on here, and vice versa. Undo our x part. Now we've got to undo our y part. Okay, and we just changed the orientation of 2 edges. Now, I guess there are other ways to do it. So let's see, we could do something like that, and then change the orientation, and that will change the orientation of 2 pieces. And I think that takes the exact same number of moves, right? So that's also 8 moves. So it's just an alternative orientation changing commutator, I guess it should be really easy to build pretty much any of them. So if we want to, let's say we want to change the orientation of this, like let's do this blue-green piece, and do the blue-green piece and this white-purple piece. So we should be able to do blue-green. No, okay, so well, without a bunch of setup moves, just ignore that. The setup moves on this puzzle are really pain in the ass. So if we want to move this edge into that spot, you know, that could involve quite a few. So we got it across. There we go. Now we got it into that spot. So I don't know. I mean, that was 5 moves. I don't know if that's the most efficient way to take that piece and put it there. Maybe there's a more efficient way to do it, but the setup moves on this puzzle are a huge pain in the ass. So this 3 cycle we did of this edge, 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 I mean, basically, if you don't have an edge in this 3, you're going to have to use a setup move. So like that piece to there, that's pretty convenient. So, you know, that's only 1 setup move. But if you want to do that piece to there, that could, you know, really involve a lot of, yeah, see, that didn't even do it. That could involve a lot of setup moves. And so you should explore options for these edges. Well, and just setup move options in general. So I think if we do something like, so let's see. So we could have put, okay. So that would have put that piece there. Okay, so let's do that setup move, and let's do that setup move. And now let's do our 1-1 commutator. Now undo setup move, and ignoring all the stuff that we broke around here, we did a 3 cycle of edge, edge, edge. So we did a counterclockwise 3 cycle of edges on the same face, and we did it in 8 total moves. So that can be really convenient to do. You know, to have multiple 3 cycles under your belt for these edges so that you don't spend, you know, a really long time finding setup moves to set up your cycle nicely. And then the other thing, so we saw how to change the orientation of an edge, and we saw how to 3 cycle the edges. The other problem is that on this puzzle, I believe it is possible, as long as you have not solved these centers, as long as you have not solved the center pieces, and sort of the plan is to solve these edges first, then it is possible to have a single edge flipped. And the reason it is possible is because when you flip a single edge, you swap these 2 pieces and you swap those 2 pieces. And a 2-2 swap can be solved via 3 cycles. So you could solve this 2-2 swap via 2 3 cycles plus a bunch of setup moves. And that would have left 2 center swapped and this edge flipped. And so what we're going to have to do is we're going to have to look out for, you know, as we get towards the end and we have an odd number of centers flipped, we're just going to count it up towards the end when maybe we have like 5 centers. And if we have an odd number, we're just going to change the orientation of one of them, and then we're going to continue cycling. Even if it breaks something we've already fixed, and we'll just have to fix it with 3 cycles. And that'll also, because the parity of, so the permutation parity of these centers is going to be tied to the orientation of these edges. Once we've solved all the edges and they all have the right orientation, then we know that we won't hit any parity in these center pieces, which will be really convenient. Okay, so I think I've beaten edges to death. And so let's see, we know how to do edges via 1-1 commutator. We know how to do, assuming it's reasonable, we know how to do that piece with a 1-1 commutator, which is going to be really convenient. Because usually a sort of a deeper piece in towards the center of the puzzle is going to be relatively hard to isolate. So, you know, finding a pure sequence for this type of piece, it could be really hard. I haven't even tried. Well, actually, you know what? I see how to do it, I think. So I think the way to do it, you do a setup move, and then you do that, undo setup move, undo setup move. Okay, so now we've isolated that piece. Now we flip it around. Redo setup move, that, undo setup move. Okay, so that is an 18 move. Now I can probably be done more efficiently than that. But that is an 18 move sequence to do a pure 3 cycle. we probably don't want to do that. We probably want to stick to this 1, 1, and that'll work for us. So basically we have to solve these pieces before we solve that piece or that piece, because solving these pieces breaks those. So let's see if we can figure out how to solve these pieces. So that's pretty much the default. I didn't have to think about that. You know, that's like one of the easiest two overlaps that we can find. So what is available to us? Well, it looks like that piece and that piece are isolated. So if I do that, and then we're undoing our x, then we undo our y. Okay, so that's a 3 cycle of both this Gigaminx corner center piece, and we'll call it this wing point piece. So that's going to solve one of them for us. It's either going to, we can either use that sequence to solve these pieces or to solve these pieces. And so if we want to solve the Gigaminx corner pieces, then we're going to have to find a pure 3 cycle for this. And if we want to solve this, then we're going to have to find a pure 3 cycle for this Gigaminx corner piece. So let's see what options are available to us. Okay, so let's go back to that 3. Basically, we have 2 pieces that are isolated here. We have to figure out how to separate these 2 if we want to find a pure 3 cycle for one or the other. So we could try moving that out of the way with a setup move. So so we want to move just this piece. So we want to get that out of the way. So we use a setup move, and unfortunately, even if we did use a setup move, it put other things that we cycled in the way. So instead of doing a 3 move, let's do a 4 move. Does that stuff still in the way? Yeah, this stuff is still going to be in the way. Okay, so that's going to be the wrong strategy. So we want to isolate either that piece or that piece. What if we do that move, and now that piece is isolated, and then that move, and then that move. Okay, so that's the y part. Now we need to undo the x part. Now we need to undo the y part, and that y part is that. Okay, so that's a 12 move sequence. It's 5, 1, I believe. So we did, no, actually, you know what? It's 3, 3. Yeah, so we did 3 moves, then we did another 3 moves, then we undid 3, for 12 moves total. And that's a nice 3 cycle of these pieces. Now, again, we always want to use the longest 3 cycles for the fewest pieces. So we have, so here's a 3, 1 sequence, 8 moves total. So that's 8 moves, and it cycles those pairs. So we have an option here. Do we want to use a 3 cycle that's pure in these pieces, which we haven't even found yet, or a 3 cycle that's pure in these pieces? Since we use 8 moves, there are 120 of these points, 60 in 2 chiral orbits. And so 120 times 8, I think, is 960. And if we did our 12 moves for these 60 pieces, that's only 720. So I think it would be much preferable to spend more moves solving these pieces instead of these pieces. So let's see if we can even find a pure 3 cycle of those pieces. Okay. We don't know how to do it here. If it were obvious, we would have already done it. So let's see if we can do it here. So we want to say, like, take a swipe out of that piece right there. Okay, there should be a setup move. Great, I think this is going to work. Okay, so let me rewind here. That's our 3. Now we do a setup move. That isolates that piece. Ignore that it's broken for a second. And then we undo our setup move. And then we undo our X part. And then now we're going to undo our Y part. Setup move, swipe, setup move. Okay, and so now we have so this is also a 3, 3 sequence to cycle, a 3 cycle of these points. So basically we can do 12 moves for the Gigaminx corners, or we can do 12 moves for these points. And as I said before, because there are more points, we'd have to do, 906, so 120 of these times 12 is going to be 900 and, no, I haven't, let me do that math. So 120 of them times 12, what is that going to be, like 1,440 or something like that? Probably not a very good idea. So if you're not following me, let me reiterate. Sorry, I told you this is going to be a stream of consciousness video, but this is the thought cycle that I go through when I'm going through and trying to figure out how to solve these puzzles. So I think the stream of consciousness is worthwhile. So that was 8 moves. We can either solve that piece with it or that piece with it. Obviously, we can't solve both because, you go to solve one, you're going to break the other. You go to solve the other, you're going to break the first. So we got to pick one. Because there are more of these pieces and the sequence is only 8 moves, we should solve these pieces with that sequence, not these pieces with it. Since we found a 12-move sequence that'll solve either one pure, if we have to do a 12-move sequence for one of these pieces, let it be the one we have fewer of. Hopefully that makes sense. Okay, so let's recap where we're at on this puzzle so far. We know how to do edges with a 1-1 commutator. We know how to do centers with a 3-1 commutator. Okay. We think we know how to do these Gigamink center, middle center things with a 1-1 commutator. But look, it breaks that piece and that piece. And we already decided that we were going to solve these later. So we could use this 1-1 commutator. We could use that 1-1 commutator to solve that piece, and then after that solve this piece. No, okay, so what we would do is we'd solve this piece first, and then we would solve that piece, and then we would solve that piece, because the sequence we have for this piece is pure. So let me show you the sequence we have. You already saw it for these two. Let me show you the sequence we have for that one, if I can remember it. Okay, so I think it did that, and then, oh, and then that, and then that. Okay? So a 3-3. Okay. I suspect that a 3-3 is probably very confusing because when I always say isolated piece, the piece has to be isolated. And so if we do that, so we did our 3 moves, and then we start our other 3 moves, neither one of these pieces is isolated. And it doesn't really look like that is isolating the piece because there's all this broken stuff. We can actually convert that 3-3 sequence into a 5-1 sequence. So the way that works is you do a setup move. That's 1. And then we do our 3. And then we undo our setup move. Oh, okay, I did it wrong. Okay, so let's figure out which setup move we need to use. So it's this orange. No, it's this orange-purple. Okay. So we're going to do our orange-purple setup move. Now we did our 3. Now we're going to undo our setup move. Now you can see that this is very isolated. Okay, so we've done 5 moves so far. Now we're going to do 1 move. Now we're going to do our setup move. We're going to undo our X sequence. Undoing it is that. Now we're going to undo our setup move. And then we're going to undo our Y part. And it's the exact same thing. You can always, as far as I know, you can always take setup moves that you were going to do in the Y and you can move them into the X. So that, instead of isolating a piece, sort of somewhat isolating it in the X part and then further isolating it in the Y part, and then, undoing X, undoing Y. I believe that you can always move the setup moves in the Y sequence into the X sequence without any problem. And I've never found a contradiction to that. You can view the sequence differently, too. So that was our 3 moves. You can view this as a setup move. That is our XP part. Then we're going to undo a setup move. So we did the conjugate sequence where we did setup move, which is X, Y part, the useful thing, and then an undo setup move, the undo X. And then we can view this as another conjugate sequence. Setup move, the useful part, undo setup move, and then setup move, undo setup move, and then setup move, undo setup move. It's really just a different way to look at the exact same sequence. And if you are able to understand why a conjugate sequence works and why a conjugate sequence is equivalent to setup moves and why the only conjugate sequences available to you are the same ones that make the only available 1-1 commutators, and you understand that if you do a setup move in the Y part, you can move it into the X part. If you understand all of that, you are well on your way to solving many, many, many very complicated puzzles, much more complicated than this puzzle. Okay, so let's recap. We can solve the edges with 1-1 commutator. We can change their orientation with an orientation changing commutator. We have figured out how to solve their parity via flip it and then do a 2 3 cycles. We know that we can solve the centers. So let's do edges and then centers. And then we know we can solve these pieces with 1-1 commutators. And then we can solve those pieces with 3-1 commutators. And then we can solve those pieces with, you can either look at it as a 3-3 commutator or a 5-1 commutator, so 12 moves. The only piece left on this puzzle is this point piece, this little center point thing. So let's see what we can do there. Just go to our default, this is going to be like one of our useful 3 sequences. Okay, well, there's the only point piece that isn't even remotely isolated. And can we do that? Well, if we do that, then, okay, so let's try that. Okay, so that broke a lot of pieces, but so it did a 3 cycle of these point pieces, these really, really, really skinny pieces in the center here. So it did a 3 cycle of the brown and the green, and yeah, okay, so there we go. So we got the brown, the pink, and the green. So we've got a clockwise 3 cycle here. And it broke other things. Can we afford to break other things at this phase? So let's see. We already know that we're going to solve edges first, and then we're going to solve centers. And then we want to solve those pieces next with 1-1 commutators. Okay, so we want to solve those pieces with 1-1 commutators, but we're not going to be able to if our 3 cycle for these pieces breaks those pieces. So we need to figure out which one to do first. And yeah, okay, so watch. If we do that, it's going to break one of those pieces. It's going to break that piece right there. And it's going to break the one over there too. So it's going to do like 2 3 cycles, which is it's just going to make a total mess. Okay. So we have a couple options here. We can solve these pieces before we solve those pieces, which it seems reasonable, or we can find a cleaner cycle for these pieces. So I already know what I think is going to be the right answer, but let's find a cleaner cycle for those pieces. And so if we do that, we need to essentially mask that off, but we also have to do it there. So what we're probably going to need to do is we're going to need to do a full 4-1. And no, it's still going to, it's just, yeah, okay, so there we could do that. Okay, so let's do a setup move, and then let's do a 1-1. Then we're going to undo our setup move. Okay, so now we have those pieces isolated essentially. We're not going to break any of these gigamix center point things, or center, middle, edge, whatever things. Okay, and then we need to redo the setup move, and then we need to undo the 1-1, undo the setup move. Okay, that was 14 moves. It was a 6-1. So we did a setup move on a 4-move sequence, and then we undid the setup move. So that was 6 moves, and then we did 1 move, and we did 6, undid 1. That's 14 total moves. That seems really bad. So what are our options available to us? Solve edges, solve centers, then we're going to solve these point pieces. So we're going to solve these point pieces by doing this. Solve the point pieces. Okay. Then we're going to solve these middle gigamink center piece things. Because it doesn't affect the point pieces, it doesn't affect anything we've already solved. Then we're going to solve these wing point pieces. And so we're going to do those with a 3-1. Okay? And so at that point, we will have edges solved, center solved, these middle point pieces solved, these middle gigaminx center things solved, these wing point pieces solved, and then the only thing left on this puzzle is going to be these pieces, and we already saw a 5-1 commutator to handle those, or that is a 3-3 commutator, which is a different way to look at the same thing, basically. So let's see that sequence again. I have to refigure it out. Okay, so that's the setup move. And then undo that setup move. I piece is isolated, so that's the Y part. Now we're going to undo the X part. Okay, and if we follow that solve order, edges, centers, middle points, middle centers, middle center edge things, wings, point wings, and then the middle corner things, we will have solved this puzzle. And I think that we will have solved it quite efficiently too. Because again, the shortest possible commutator you can have is 1-1. The next shortest possible commutator is 3-1. And so let's see, we have 1-1 for the edges. We have 3-1 for these points. We have 1-1 for those middle edges. Then we have 3-1 for these wings. And then the only piece that we have a longer sequence for is these 5-1s for, oh, I forgot the 3-1s for the centers. And then these gigaminx corner piece, center piece things are the only things we have like a relatively long commutator for, a 5-1. So I think that that's probably going to be the optimal solve order. Now, if you recall, I noticed in the beginning that we have a left-handed version and a right-handed version of these. So if we do the sequence that I've been saying, this 3-1, that solved the right-handed version of the pieces, the right chirality. We need to solve the left chirality too. The only way to do that is to apply the mirror sequence. So we were doing that, but instead we're going to have to do this. So we're doing the mirror sequence. And if the previous one did the right, then this one must do the left. And indeed, we did the left chiral wing point pieces. So I think that that's all that there is to say about this puzzle. Doesn't look like there's any orbits or anything like that. We didn't notice any funky business. So what is the solve order for this puzzle? We are going to, let me run through each one of the sequences in turn. We're going to solve edges via 1-1. Edges have orientation available to them. So we're going to fix parity by just flipping a single edge and then 3-cycling this 2-2 swaps and resolving it. And then to flip the orientation of two pieces, there's lots of different ways to do that. Here's one of them. That's 1-3. Flip the orientation of two edges. So that's everything you need to know about how to solve edges. Now we're going to solve centers. There's centers. Okay. Then we're going to solve these point pieces, those middle point pieces. Again, we're going to use a 3-1. So ignoring all the broken stuff, we did the purple, blue, light blue 3-cycle. Then we're going to solve these Gigaminx middle center edge things with a 1-1. Then we're going to solve the right-handed point pieces. Then we're going to solve the left-handed point pieces. Oh, start this way. Okay, and then we're going to solve the Gigaminx middle center corner things. And so we're going to do a 5-1 for that, because I think it's easiest to think about it in terms of a 5-1. So that was the 5, here's the 1. Now we're going to undo the 5. And that is going to solve this puzzle. There are no other pieces left on this puzzle. There's no other funky business on this puzzle. That should do it. I guess the only type of piece that could possibly have an orbit is, well, I don't think any piece on this puzzle could have an orbit. So I guess the way to verify is to see if we can put this piece in that spot. If we can put this piece in that spot, then sort of via induction, then we could by the sort of the reorientation principle, then we could put it in that spot, and then that spot, and then that spot, right? So if this piece can go in the spot next to it, then it can go in all spots. And we already know that if this piece can go in all spots, and we do a move, we can move it to this face, and then it can go in all spots on this face. And so really, I guess it's induction or, well anyways, it would essentially prove that there are no orbits for these pieces. So the question is, can we put that piece in that spot? Let's find out. It would be nice if these were like uniquely labeled, so that like they had a unique color. So instead of what I'm going to do is I'm going to move all the other white pieces out of the way. There are no white pieces left on this face. Now we're going to try to remember the orientation of this face, the white, and we're going to try to get it into that spot. And the way we're going to try to remember that this is the white face is if you look over here, we're going to keep the yellow face opposite if possible. So I have not actually tried this. Did that move it over? I can't remember. So we put it right there. Was it right there? I cannot remember. So let's do some undos and see if it comes back to right there. It did. It came back to right there. Let's make sure that we are actually dealing with the piece that I was thinking we were dealing with. Indeed, that proves that there are no orbits in these pieces. And again, let me reiterate, if we can move that piece to there, then via the reorientation principle, then we could move that piece to there, which is the same piece. And via, I think, induction, it would go on every single face, or every single location in this piece. And because we can move a piece to another face, and it could go anywhere there, and it could move, again, move a piece to any other face, it could go anywhere, I believe that that proves that there are no orbits. I guess the only other thing, well, okay, so that doesn't actually prove it. Because we know that the white pieces can go on the green face, right? But we don't actually know if the white pieces can go on this blue face at all. So if we move a white piece to the green face, it doesn't actually move a white piece to the blue face. Can we move a white piece to the blue face? Indeed we can. Okay, there are no orbits on this puzzle. Or at least there are no orbits in these pieces. And we already know there are no orbits in these pieces other than their Sherrill versions. And there are no orbits in the edges, because we saw we could move an edge to an adjacent location. And we know there are no orbits of the centers. And we know there are no orbits of these point pieces. Yeah, we have to know that. So are there any orbits of these pieces? That piece. So can we move that piece to any other, well, to like an adjacent location? Well, we moved it across, but I don't think that's good enough proof. Yeah, okay, so let's see. If we move it across, so it skips a piece, then it skips a piece, then it skips a piece. Yes, so via induction, or whatever that principle is, there are no orbits. So there are no orbits on this puzzle at all, other than the Cheryl version, the right-handed and left-handed version of these points. So again, I really think that, I mean, this puzzle might seem complicated, but I hope that after I've broken it down, it won't be complicated. I think it looks to me like a medium difficulty puzzle. All the sequences are relatively short, except for the last one, which is a 5-1, which is 12 moves. So the only thing that makes this puzzle hard is that the setup moves are going to be a little bit challenging just because it's an edge-turning puzzle. And it looks like total chaos when it's scrambled. And it has a lot of pieces. Just, there's, 60 of that piece, and that piece, and 120 of those pieces, and 30 edges, and 12 cents. Like, there's just a lot of pieces on this puzzle. So, based on what I've shown you, I think that this puzzle would take me between 2 and 3 hours to solve. And that's not because it would be a whole lot of thought or anything like that. It would just take a long time to sort of find the setup, to find the setups to do the cycles, and to just cycle the sheer number of pieces that it has. So unless you're Schuma or Michael Gottlieb or someone like that, who is just a setup machine, it's just going to take a long time to solve this puzzle. And so I think it's a beautiful puzzle. I'm probably going to go ahead and solve it. And I encourage you to. But I hope that you take the principles that I have discussed in this video and you go and you look at other puzzles under the same lens that I've used here. And then you'll be able to see, how do we solve this piece, that piece? How do we use non-peer commutators, and how do we layer peer ones on top of it, or less non-peer commutators on top of it? And then we whittle this puzzle down until there's like only one piece type left, and then do a peer commutator with that piece type. And that principle just applies to every twisty puzzle there is. And what the cool thing is this one has Cheryl pieces. It doesn't have any orbits, so you don't have to deal with that. That's kind of nice. So again, I really think that that's kind of all to say on this puzzle. I hope this video was useful. I know it was terribly long. Thank you for watching.